Very good evening, everyone, and welcome to the NPTEL's fifth live interactive session on the course Mechanical Behavior of Materials. The course instructor for this course are Dr. Shashank Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering, IIT Kanpur. Myself, Shubham Jaiswal, I am additional TA. I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So, in this live interactive session, we will be discussing some concept related questions that will help you to solve your weekly assignments. Okay. So, in today's session, first we will quickly recapitulate what are the things that we have seen in week 5. Then, followed by some concept related question. And if the time permits, we will try to solve the week 5 assignment. So, let's not wait further. We'll start. So, last week, we started with the concept of plastic instability. So, what is plastic instability? So, plastic instability, it is a condition where plastic deformation would continue under the falling load of pressure. So, if the load decreases, but still the deformation will be going on. So, that condition is known as the plastic instability. So, load of pressure. So, if we are performing uniaxial testing, at what point it should start? So, generally, in uniaxial testing, the instability point or the deformation occurs at a local regime, and at that point, generally the uniform elongation that is there, it will ceases, and the force it will be maximum at that point. So, in local regime. Also, the uniform elongation at this particular point is ceases. So, also the fourth point that we can talk about plastic instability, that at the point of instability, the force is maximum or the df equal to 0. So let me draw the tensile strain curve. Let's say this is my tensile stress strain curve. So here we can represent this point where the slope 0 of df is 0, and this is our uniform elongation. So if we consider the power law, sigma to epsilon to the power n, and the force is nothing but stress multiplied by area. So here I am considering the effective stress as we are talking about the uniaxial condition. So according to point of instability, at point of instability, df equal to 0. So this should be there. That is sigma dA plus A d sigma bar should be equal to 0. So if I rearrange these things, so I will get some equation something like this. A. And if we compare it with the strain, so we can also write d minus dA upon A equal to dl upon L. So let's say this is my equation 1. Okay. Sorry, sir. Let me correct. So dA upon A. Also we know the strain, the change in strain, d epsilon, is nothing but minus dA upon A. It is also equal to dl upon L. So let's say this is our equation 1 and this is our equation 2. So if we put this value from equation and 1 and 2, so what we will get from equation 1 and 2, d sigma bar upon sigma bar equal to d epsilon bar. So d sigma bar equal to d epsilon bar should be equal to effective stress. This is the condition for plastic instability. Let's say this is our equation 3. So now if we want to find out the value of exponents, work hardening exponent n, then how we can calculate it? So let's say this is our d sigma upon d epsilon. It should be equal to kn epsilon to the power n minus 1. And d sigma upon d epsilon, it is nothing but sigma bar. It is kn, and our effective stress should be equal to the effective strain. Okay, means it should follow the power law, and the strain will be effective strain. That is kn. Sorry. K epsilon bar n is equal to kn epsilon n upon epsilon. So these terms gets cancelled out. So our exponent n should be equal to the uniform elongation. So if I show here, so epsilon is equal to u. Okay. So from this, what we can say that as the value of n increases, the total elongation increases. And why the total elongation will increase? Because the increase in n will result in increase in uniform elongation. So increases. Total elongation increases since the uniform elongation is increasing. Okay. Then after that we have seen a thing, the concept known as consider criterion. So if I draw a stress strain curve, okay, something like this, two stress versus two strain curve. Okay. Okay. And if I draw a tangent or the slope of at UTS, okay. So this should be equal to 1, and this is our epsilon bar equal to n, and here it is d sigma upon d epsilon. So this is the value of sigma. So if we geometrically represent it, so what we will get, d sigma upon d epsilon equal to sigma upon 1. And if you plot the two stress and its slope together, so we will see something like this. Let's say this is two stress. So if I draw the slope, so here you can see the slope is continuously decreasing with increase in the strain. So at this point, these two curves are intersecting. This point is nothing but the point of instability, or the instability instant, or here from this point onwards the necking will start. Instability instant or start of necking. Okay, so this is slope, and let me write d epsilon upon. Okay. And this curve will follow the equation sigma equal to k epsilon to the power n. And usually the value of n ranges from 0.1 to 0.6. N ranges from 0.1 to 0.6. Okay. So after this, we have seen the how the n value affects the work hardening rate. Okay, means how it gives the information about the work hardening rate. So let's say I have a material with a n value low and n value high. So let me draw the curve. So this is with the lower n, and this is with the higher n value. So from this curves, what we can see, if n is low. So if the n is low, the work hardening rate is initially very high, but after some times it decreases rapidly with the increase in strain. So rate is initially very high, but rate decreases rapidly with the strain. Now, suppose if the n value is low, if the n is higher, so what will happen? From this curve, you can easily say that the work hardening is initially less, is less rapid, but it will continue to rise to a higher strain level. So if n is high, work hardening is initially less rapid, but continues to rise to high strains. Okay. So these are the things we have seen in the plastic instability. So after that, we have seen the new topic called the effect of strain rate. So what will happen if the strain rate is high or low? So like if I increase the strain rate or the rate of deformation, so how it will affect the flow stress? Okay, let's see. So the effect of strain rate, also known as rate of deformation, and it is given by equation del ln sigma upon del ln sorry del epsilon equal to m. What is m here? Here m is for the strain rate sensitivity. So here m is strain rate sensitivity. So there is one equation similar to the power law, but here it talks about the effect of strain rate and strain rate sensitivity on the flow stress, and it is given by sigma equal to c epsilon means strain rate to the power em. Let's say this is our equation 1, and also the value of em usually ranges from 0 to 0.03. 0.03. Okay. So if you want, from this equation we can say, if appreciable changes to be observed in the material or in the flow stress, then strain rate should be appreciably significant, or it should be higher. So was a significant change in flow stress. Okay. And also we have seen that the strain rate sensitivity parameter M, it is dependent on the temperature. So for the operating condition, that is T is greater than 0.5 Tm, or the homologous temperature, if homologous temperature is 0.5, then M ranges from 0.1 to 0.5. So these are the things we have seen in the effect of strain rate. So now if I want to increase the, if I want to measure the strain rate sensitivity parameter M, so how I can measure it? Any guesses? So we can measure the value of M by in two ways. One is performing the uniaxial testing with two different strain rates, or two different tests. Okay, with two different strain rates. And second one is performing the one test itself, but with the two strain rate. That is the strain rate jumping test. So let me draw. So here, let's say I perform first test with the strain rate epsilon 1, and the second test with the strain rate epsilon 2, such that epsilon 2 dot is greater than epsilon 1 dot. So what I will do, so at this point, means at which what we are considering here, the strain in both the cases is same. So if I apply the equation here at point A, and means for curve A and for curve 2. So for curve 1, it will be sigma 1 C epsilon dot M to the power M, and for curve 2, sigma 2 C epsilon 2 dot to the power M, and it will, and in this way we can calculate the value of M. And the second way is by performing the jump test. So let's say for this much elongation, I have performed the test with the strain rate of epsilon 1 dot, and then with the strain rate of epsilon 2 dot, such that epsilon 2 dot is greater than epsilon 1 dot. So here also we are considering the same thing. So now if I divide these two equations, that is equation A by B. So what I will get? I will get some equation something like this: sigma 1 divided by sigma 2 to the strain rates to the power m. And if I want to find out the m, so I will take a logarithm on both sides. So I will get equation something like this. And this way we can calculate the value of m. And also we have seen the effect of temperature on the value of m. And what is its significance? If the m value is very large, so what will happen? It will lead that material to the superplasticity. Here you can see how the m value is dependent on the temperature. So let's say this is my m value. This is 0.2. So up to T by Tm equal to 0.5, the variation in m is very small. But as soon as it crosses the 0.5, so it will rapidly increases. And this will lead to the superplasticity. So let me write down the significance. M leads to superplasticity. So what is superplasticity? So it is a deformation that results in very large elongation at very low flow stresses without the failure of material. So that result in very large elongations at low stresses and without the failure of material. And what will be the value of strain at this instant? So the material will expand means by 2000%, or approximately we can say that it will elongate 20 times its original size. So is approximately 2000% or 20 times we can say. Okay. So this is the definition of superplasticity. So then after that we have seen what are the necessary conditions for the superplasticity. So can anyone tell what are the necessary conditions for superplasticity? The first condition is that the material should be fine, means its microstructure should be fine grained, and it should have a equiaxial structure. Extremely fine grained and equiaxial structure. The second condition is that the temperature should be relatively high. It should be around 0.4 times of means 40% of your melting temperature. So and the third, that is the for superplasticity, low strength rate are required. Low strain rate. And the fourth condition is that the microstructure should be stable in that temperature range. So stability of microstructure. Okay. Then after this, we have seen the combined effect of strain and strain rate on flow stresses. So effect of strain and strain rate. And what is the necessary condition for this case? We are assuming the temperature remains constant. So the equation is given by sigma c epsilon to the power n and strain rate to the power m. Assuming T is constant. So after that, we have seen the effect of temperature on the flow stresses. So how does the temperature affects the flow stresses? Means whether it will increase, decrease, or remain same. And what about the ductility? Any guesses? Effect of temperature. So with increase in the temperature, the flow stresses decreases, but the ductility increases. So increasing strain rate have the same effect as that of our decreasing temperature. So let's say this is my epsilon and this is my sigma. So this is increasing strain rate or decreasing temperature. And the effect of temperature, when we assume the strain rate and strain remains constant, is given by sigma equal to C2 exponential of Q by RT, where Q is the activation energy for the plastic flow. Plastic flow. Okay. So this gives the effect of temperature. So now, if we see at the combined effect of strain rate and temperature on the flow states. So strain rate and temperature. So we already talked about that. The decrease in temperature has the same effect as in increase in the strain rate, and it is given by the equation that is strain rate, or also known as creep rate, equal to A exponential minus Q upon RT. So here in this equation, A is exclusively function of flow stress. And here Q is nothing but the activation energy for plastic strain. So, and if we rearrange, then we will get the Zinner-Holloman equation, that is Z is equal to strain rate into exponential of Q by RT, where R is the gas constant and T is the temperature, and Z is Zinner-Holloman parameter. So this equation gives the combined effect of strain rate and temperature. So after this, we came to new concept that is known as the dislocation. Dislocation. So in dislocation, we have seen first thing, that is the weakening of crystal, and in that we have derived the equation for the theoretical shear stress of the material, shear strength of the material. So let's say this is my let's say these are the atoms. Okay, so let me write down. Let's say this is A layer, this is B layer. Okay, so this is A layer and this is B layer. So in generally we have seen that the material deformed due to the shearing action or the shear stresses due to the slip. So here we can see the slip plane. So let's say this is my slip plane. Okay, so let's say this is my B layer and this is my A layer. Okay, and this is my I am applying shear stress on it. Okay, so if I draw the energy plot for this condition, so how it will look like? So let's say this is X, and X is nothing but the distance that the atoms are being moved. And B is the distance between the equilibrium position. So let's say I have two equilibrium position. That is, if B is on the left side of A, then we have one more position, that is when B is on exactly top of the A, and let's say this is A and B is to the right of A. So these are the two positions. So at this position, the energy will be minimum. And okay, and at the second position, that is when A, that is when B is left to that of the A. So if I draw the energy curve, I will get energy curve something like this. Okay, so this is energy curve. So, and if I draw the shear stress curve, how the shear stress is changing. So it will be something like this. Let's do this down. So it will vary something like this. Okay, let's do this. So as from this figure, you can see that these two curves are having the nature same as that of sinusoidal curve. So I can write tau is equal to tau max sine 2 pi x by b. And what is b here? B is the distance between the equilibrium position. So let me. This is b. That is the distance between equilibrium position. So here, and the tau max is the theoretical strength of the crystal. Theoretical strength of the crystal, and x is distance the atoms are being moved. And b is the distance between the equilibrium position. So if the distance that is being moved by the atom is very, very less than the distance between the equilibrium position, so we can write this equation tau equal to tau max 2 pi x by b. Also, we know the x by b is nothing but the shear strain. And also we know the shear stress can also be written as G into shear strain. And if we put this value in this equation, that is tau equal to tau max into 2 pi x by b, so we will get the final equation something like this, that is the theoretical strain should be equal to G upon 2 pi. So this is the theoretical strength. And for the then some people did the experiment and they derived the true realistic expression, and that is tau max equal to G upon 30. So this is a true realistic expression. So the assumed model of the deformation was incorrect, means it was not giving the correct strength values. So the assumed model of deformation is incorrect. So then people came to know that there are something more happening inside the material, and they said that this is due to the dislocation. So then we have came across the concept of observation of dislocation. So how we can observe the dislocation? So we will polish the sample and we will slightly deform it. So we will say the some steps on it, and that steps is nothing but the dislocation. So slightly polish, slightly deformed, polished samples. Okay, so let's say this is my polished sample. These are the atoms. Okay, so if I slightly deform it, so what will happen? The steps will be generated here, and this step is observed as a line, and this is our dislocation. Okay, so this is about the observation of dislocations. So we can see the dislocation in by naked eyes as well as in the optical microscope or some high resolution microscope like scanning electron microscope, etc. So then we have seen the dislocation fundamentals, and in that first we have seen the edge dislocation. What is edge dislocation? It is nothing but a extra half plane added in the material. So in the sequence of atoms. So physically, edge dislocation is extra half plane. Okay, so let me draw. So let's say this is perfectly ordered crystal, and in which we are adding one extra plane. Okay. So I'm just representing the atoms here, but these are nothing but a planes. So okay, let me draw the plane. Okay. So let's see. So here you can see that this is the extra half plane that is being added. Okay, so every dislocation has one line vector and one is the slip vector. So line vector and slip vector. That is B1. And what is this slip vector? It is the shortest lattice translation vector. Then we have seen that, let's say this is my line vector. Okay. And this is my shortest translation Burgers vector. Okay. So we know how to find out the Burgers vector and draw the Burger circuit, etc. That these are the things we have seen in the lecture itself. So if I talk that physically the edge dislocation is the extra half plane, but practically it is only a line. Practically it is only line. So this is the thing we have seen about the edge dislocation. The second, that the thing that we have seen is nothing but a screw dislocation. So like the edge dislocation, here we have the second thing, screw dislocation. And in all this thing, we are using the sign convention, that is right hand front to start. So right hand front to start convention we are being used. Okay. So according to this convention, the definition is so like the Burgess like the edge dislocation, that is we have positive edge dislocation and negative dislocation. Similarly, in screw dislocation, we have the right-handed screw and left-handed screw. So what is the right-handed screw? So it advances one plane after the clockwise circuit if you are following the RHFS, and if it goes back one plane after the clockwise circuit, then that dislocation is known as the left-handed screw dislocation. So okay, so let me draw the schematic for you. So so we have right-handed screw or RH screw. Okay, right-handed screw. So what is definition? It advances one plane after clockwise circuit, and here left-handed screw or ELH is nothing but it goes back one plane after clockwise circuit. Okay, so like this, if we are considering and the RHFS, so here you can see that the line vector and slip vector are perpendicular. So sorry to I forgot to mention, and Burgers vector are perpendicular. And here, let's see how it will come in the screw dislocation. So first, what we need to do, we need to take our hand and we need to keep our thumb in the direction of direction of our line vector, or also known as sense vector, and then we will do the clockwise circuit. So here, let's say I am going. This is my start point. Okay, so I am going 2 steps down, then 2 steps towards left, 4 steps towards left, then I am moving 4 steps up. Then as I moved 4 steps towards left, now I need to move 4 steps towards right. So now this left movement and right movement is same. Now I need to check whether the movement, that is the here I went for 4 steps upward. Now here I need to move 4 steps downward. So here this is 1 and this is 2, and already we have moved 2 steps down, and but these 2 points are not coinciding. So it means some dislocation is there, and this is the screw dislocation. And here let's say this is my U bar and this is my Burgess vector. So here you can see, and this is my finishing point and this is my start point. So here, as you can see, that after the clockwise circuit, the one, it is going back one plane. Okay, one plane is, it went, it shifted by one plane. Or here you can see this much it has traveled. Like it goes back one plane after a clockwise circuit. So this dislocation is left-handed. And here the line vector and Burgers vector are parallel. So these are the things we have seen about the edge dislocation and screw dislocation. So after that, we have noted down some characteristics of the Burgers vector. So what is Burgers vector? It is the shortest lattice translation vector. Okay. Now, the second thing, that is, it is also same as the slip vector. What is the fourth point that we have? Third point that is here. It is the direction along which the nest displacement occurs. Also, the fourth point about the Burgess vector, that uh, it is the vector that closes the Burgess circuit. Vector that closes Burgess circuit. Okay. So this is the quick recapitulation of the what are the things that we have seen in the week 5. Okay, so now we will move towards the solving some concept related problem. So let's not wait. Let's move further. So this is the first question, that if a metal is subjected to high strain rate deformation under tensile loading at room temperature, which of the following will hold true? More than one answer is correct. The flow stress of metal will increase, the flow stress of metal will decrease, work hardening rate of metal will increase, or work hardening rate of metal will decrease. Anyone? So let's see. So I'm drawing the stress strain curve at two different rates, and according by seeing this, and see if you can answer. So let's say this is at epsilon 1 and this is epsilon 2 and epsilon 2 dot is greater than epsilon 1. Now, see. Anyone? Please try to answer. So let's see. So let's assume the uniform strain in both the material. So now you can see that the higher strain rate has higher flow stress. It means the flow stress of metal is increasing. So here, this one is correct. So if the flow stress of metal will increase, then the second, by default, it will be wrong. This is not correct. Now, the work hardening rate of metal will increase. Here, from the figure, you can see that here, the work hardening rate is increasing with the higher strain rate. So, this one is also correct. So, the fourth one will be the wrong one because the what they are saying work hardening rate of the metal will decrease. So this will not be the correct option. So only first and third one will be the correct one. So let me write down. That is work hardening. Now moving to the second question. That is the flow curve of a metal is given by sigma equal to 250 epsilon to the power 0.3. Then what they are asking, the maximum true strain beyond which the necking occurs will be. So they are asking us to find out the true strain beyond which the necking should occur. Anyone? Please try to answer. So what they are saying, they have given the equation that is sigma equal to 250 epsilon to the power 0.3. So here, if we compare this equation with the sigma equal to k epsilon to the power n, so k is 250 and n is 0.3. Okay. So we know at the point of necking, at point of necking, df should be 0 or d sigma bar by d epsilon bar should be equal to sigma bar. This is the condition for plastic instability or beyond from which the necking is the necking will occur. So if I take a derivation, that is, if I follow this condition, so it will be sigma bar equal to n k epsilon to the power n divided by epsilon, and sigma bar is nothing but K epsilon bar by N equal to N K epsilon bar by N or equal divided by epsilon. So here this gets cancelled, and what will remain with the, that is epsilon is equal to En. So what does it implies? That uniform elongation or the maximum strain is similar to that of the N. So N is equal to 0.3. So epsilon equal to 0.3. So here we can write 0.3. Also, no need to derive this much in the very beginning. While we quickly recapitulate letting the things, we have seen that at necking epsilon is equal to N. We have already derived this in the very beginning. So no need to do this much calculation. You can, by simply applying the concept, you can get the answer. Okay. Now moving towards our third question. The strain rate dependence of zinc alloy can be represented by sigma equal to C strain rate to the power m, with m being 0.07. What is the ratio of flow stress at epsilon equal to 0.10 for strain rate of 10 to the power 3 to that of for a strain rate 10 to the power minus 3 per second? Repeat the same for the low carbon steel with m equal to 0.01. So they are asking for the flow stress, ratio of flow stress at two different strain rate. So can anyone solve this and tell me the answer? Please try to answer. So let's see. So here, what they are saying, they have given the equation sigma equal to C epsilon dot to the power m, and they have given the values of m equal to 0.07 for zinc alloy and m equal to 0.01 for low carbon steel. And what they are asking us to find out the sigma upon sigma 2 ratio. Also, they have given the two strain rate, that is epsilon dot 1 equal to 10 to the power 3 per second and epsilon dot 2 equal to 10 to the power minus 3 per second. And they are asking us to find out the ratio of flow stress at two different strain rate. So let's say for sorry. So for zinc alloy and heat. Okay. So let's put the value of first strain rate. So we will get equation like sigma 1 C epsilon dot to the power m is sigma 2 equal to C epsilon dot to the power m. So if I consider equation 1 divided by 2, so I will get sigma 1 divided by sigma 2 equal to C epsilon dot 1 to the power m divided by C epsilon dot 2 to the power m. So this C gets cancelled, and now we will left with only sigma 1 divided by sigma 2 equal to epsilon dot 1 divided by epsilon dot 2 to the power m. So if I put the value, so it will be 10 to the power 3 divided by 10 to the power minus 3 to the power 0.07. If I solve, so I will get answer something around. Please tell me the answer. So it should come around 2.630. So this is the ratio of flow stress when we are performing the uh, test at two different strain rate. Okay, so this is for zinc color. Now, what they are asking? They are asking us to do the same for low carbon steel. So for low carbon steel. So sigma 1 equal to C 10 to the power 3 divided by 0.01, and sigma 2 equal to C 10 to the power minus 3 to the power 0.01. So here, if I do equation 1 divided by 2, sigma 1 by sigma 2 is equal to C 10 to the power 3 to the power 0.01 divided by C 10 to the power minus 3 divided by 0.01. So this C gets cancelled, and now we left with the answer, that is sigma 1 by sigma 2 is equal to 10 to the power 6 to the power 0.01. How much it is? Sigma 1 by sigma 2. So it should come around 1.148. So this is the answer for second part. Okay. Now moving towards the next question. That is, what they are saying is that for an aluminum alloy under a constant load, the strain rate increased by a factor of 2 when the temperature was increased from 71 degrees Celsius to 77 degrees Celsius. Find the activation energy. So they are asking us to find the activation energy in this question, and they are saying that the strain rate increased by a factor of 2 when we are increasing the temperature from 71 degrees Celsius to 77 degrees Celsius. So please try to solve this question. Sorry. So let's solve this together. So what are the things that has given in the problem? Like it is the temperature, that is T1 is 71 degrees Celsius. Convert it to the Kelvin. So 71 plus 273 gives us 344 Kelvin. Similarly, T2 is 77 degrees Celsius. 77 plus 273 gives us 350 Kelvin also. So now here they are talking about the strain rate and the temperature. So now we need to consider the equation which considers the combined effect of strain rate and temperature. So what is that equation? It is epsilon dot equal to A exponential of minus Q upon R by T. So what is they are asking us to find out the value of Q. R is the gas constant and it is equal to 8.314 joule per mole Kelvin. Temperature is also given and they have also given the ratio, that is strain rate 2 is 2 times of strain rate 1. Okay, only the unknown here is A and Q. So if I write down the equation for two different strain rate, so it will be something like this: A exponential minus Q upon RT1, and similarly epsilon 2 A exponential minus Q upon RT2. This is equation 1 and this is equation 2. So now if I take a means if I divide the equation 1 by 2, so equation 1 divided by equation 2, so what I will get? Epsilon 1 dot divided by epsilon 2 dot is equal to exponential minus Q upon RT1 is equal to exponential Q upon minus Q upon RT2. So if I take this denominator term to the numerator, it will become positive. So what we will get? We will get some equation something like this: epsilon 1 dot divided by epsilon 2 is equal to exponential Q upon R exponential of Q upon R into 1 upon T2 minus 1 upon T1. So if I take a log on both sides, so what we will get? ln epsilon 1 dot epsilon 2 dot equal to Q by R 1 upon T2 minus 1 upon T1. Is it not? So now if I rearrange this equation to find the value of Q, so I will get equation something R ln epsilon 1 dot divided by epsilon 2 upon 1 upon T2 minus 1 upon T1. So let's say this is our equation 3. So now if I put the values of each and every term in equation 3, so we'll get like Q equal to 8.314 into ln of 1 by 2 divided by 1 upon 350 minus 1 upon 344. So if I solve this, that is 8.314 into ln of half, so it will be around minus 5.76, and the denominator term, that is 1 upon 350 minus 1 upon 344. So it will be around minus 4.98 into 10 to the power minus 5, and this should be equal to, that is 5.76 divided by 4.98 into 10 to the power minus 5. So it should be around 115.6 kilojoule. So this is our answer. They have asked us to calculate the activation energy. So it is how much? 115.6 kilojoule. So the similar question here comes, that is the two tension tests were made on the same alloy, but a different strain rate. Both the curves were fitted to a power law strain hardening expression of the form sigma equal to k epsilon to the power n. The results are summarized are as follows. Assuming that the flow stress at a constant strain can be approximated by the law, sigma equal to c strain rate to the power m. And they are asking us to determine the value of m. And they have given the parameter, that is, they have given strain rate, strain hardening exponent, and constant k for both the states A and B. And they are asking us to find out the value of m. So please try to solve. So let's solve this. So first we'll write down what are the things that has been given in the problem. So first thing that they have given is the strain rate, that is epsilon dot. The second thing that they have given is the strain hardening exponent, that is n. And they have given the value of constant k for both the test A and test B. So it is given 0.22. Okay. And the K is 402 and 412. So in both the cases, the strain hardening exponent is same. So now if we assume the strain in the both the states is same, so means if we apply the power law at the same strain level, so what we will get? So let's say this is first test is sigma A equal to Ka epsilon n and sigma B is equal to Kb epsilon n B Na. So Na equal to Nb equal to how much? It is 0.22. So now let's say this is our equation 1 and this is our equation 2. So now if I divide equation 1 by 2, what I will get? Equation 1 divided by equation 2. So let's write down that is sigma A upon sigma B is equal to Ka upon Kb into epsilon n upon epsilon n. So here, as these two terms are same, this will get cancelled out. So only we left with sigma A upon sigma B is equal to K is how much? Ka is 402 and Kb is how much? It's 412. So we'll get sigma A upon sigma B equal to 0.975. So this ratio we got. Okay. So now let's consider the second equation, that is the effect of strain rate on the flow stresses. So now applying sigma equal to C epsilon to the power m. So we'll get sigma A equal to Ca. So C epsilon dot A to the power m. This is, let's say this is our equation 3, and sigma B equal to C strain rate of B to the power m. Let's say this is our equation 4. So now if again I do like equation 3 divided by equation 4. So what we will get? Sigma A upon sigma B equal to C epsilon dot A to the power m divided by C epsilon dot A to the power epsilon dot B to the power m. So this CC will get cancelled out, and we know the ratio of sigma A by sigma B. So how much is this? That is 0.975 equal to epsilon A upon epsilon. So let's me put the value of epsilon A and epsilon B. So how much is the value? So how much is the value? Oh shit. So it is misbehaving. Okay. Okay. So here epsilon A is 2 into 10 to the power minus 3, and for epsilon B is 10 to the power minus 1. So let me write down. That is 0.975 equal to 2 into 10 to the power minus 3 divided by 10 to the power minus 1 to the power m. So if I take a log on both sides, so what I will get? ln 0.975 divided by ln of 2 into 10 to the power minus 2 equal to m. So if we solve this, so we will get m somewhere around 0.006. This is our answer they asked us to find out. Okay. Now, moving towards the third question, that is here. They are asking like, if the true strain curve is given by the equation sigma equal to 1400 epsilon to the power 0.33, where stress is given in the megapascal, what is the ultimate tensile strength of the material? So they are asking us to find out the ultimate tensile strength of the material. Please try to solve this one. So let's try to solve. So what are the things that has been given in the problem? That is sigma equal to 1400 epsilon to the power 0.33. So what they are asking us to calculate the ultimate tensile stress of the material. So both the true and the engineering. So we need to find out S ultimate. Okay. And sigma ultimate. So if we need to find out the ultimate strength, so we have the equation, but we don't know the strain value at the ultimate load. So at as here you can see in this graph, okay, sigma equal to epsilon. So at maximum load, UTS is there, and from this point onward, the necking will start, or this is the point of instability. So in this condition, this is uniform elongation EU is nothing but same as our strain hardening exponent M. So the uniform elongation at maximum load is epsilon u equal to n, and which is equal to 0.33. So if I put this value here, that is sigma u equal to 1400 epsilon u 0.33, which is equal to 1400 into 0.33 to the power 0.33. So we'll get true strength somewhere around 971 megapascal. Okay. So now we need ultimate tensile strength. Okay. So we know the equation that the true strain is given by ln 1 plus E. And the true stress sigma is equal to S 1 plus E. So here I am considering ultimate. So this will be ultimate. And this will be our EU. So here in this equation, if I rearrange, so what I will get? So 1 plus E should be equal to exponential of epsilon. So if I rearrange all the things in this equation, so that is sigma u equal to SU. 1 plus is how much? Exponential of epsilon. So if I put the value of SU is 971. Sorry, sigma U is 971. SU is unknown. SU exponential of 0.33. So we'll get ultimate strength somewhere around, that is 971 divided by exponential of 0.33. So it will come out near to 698 megapascal. Okay. So this is all about the fourth question. Now moving towards the next question. So the next question is like this. A material has a true stress strain curve that can be approximated by sigma equal to y plus a epsilon. Express the uniform elongation EU in terms of the constant a and y. So this is the equation of straight line. So we have some graph something like this. This is the graph, and it is following the equation sigma equal to y plus a epsilon. So and they are asking us to find out the uniform elongation in the form of constant a and y. So it is somewhat similar to the previous question. So please try to answer it. So we have the equation sigma equal to y plus a. So I'll give you the hint. So try to solve this. So when the maximum load reaches, that is the point of instability. That is sigma d sigma upon d epsilon should be equal to sigma. Now try to solve. So now if we try to take a derivative of sigma, if the given equation with the strain, so what we will get, that is sigma is nothing but equal to a. Okay, so from this equation. Also, if we put this value in this equation, so we'll get a equal to y plus a epsilon. So if we rearrange, so it will be a minus y upon a equal to epsilon. Is it not? So this will be 1 upon 1 minus y upon a equal to epsilon. Now we know that true strain is nothing but ln of 1 plus e. So exponential of e epsilon should be equal to 1 plus e, and e equal to exponential of epsilon minus 1, and epsilon is how much? It is 1 minus y upon a minus 1. So this is the value of our uniform elongation. Okay. So now here comes the next question. So the creep strain rate of polymer is given by the expression epsilon dot is equal to 4.5 into 10 to the power 11 exponential minus 100 kilojoule divided by kilojoule per RT, where T is the temperature in kelvins and R is the universal gas constant. How much time will it take for rod of this polymer to extend from 10 mm to 15 mm at 1100 degrees Celsius. So let's solve. So what are the things that in here? The initial length is 10 mm and it will move to the length of 15 mm at temperature T equal to 100 degrees Celsius. And they are asking us the time that will be taken by this rod of polymer to extend from 10 mm to 15 mm. So if we find out the strain in the material, that is final length minus initial length divided by L1. So it will come somewhere around 0.5 mm. So this is the value of del epsilon. Now they have asked us the equation strain rate, and they have given the equation strain rate equal to 4.5 into 10 to the power 11 exponential. They have given the value of Q as 100 divided by RT. So now if we put all the values, so we'll get a strain rate 4.5 into 10 to the power 11 exponential of minus 100. They have given this value in kilojoule. Now we will need to convert it into the joule because we are keeping universal gas constant in terms of joule. So all units should match. 8.314 into temperature is 100 degrees Celsius, which is equal to 373 Kelvin. So 373 Kelvin. So if we find out the value of strain rate, so it will be somewhere around 4.457 into 10 to the power minus 3 per second. So this is the value of strain rate, and strain rate is nothing but del epsilon upon dt, which is strain per unit time. So we know the value of dE, we know the value of dF strain rate, so we can easily calculate the value of dt, that is the time taken by this polymer rod to extend from 10 to 15 mm. So dt is equal to del epsilon upon epsilon dot, which is nothing but del epsilon is 0.5 divided by 4.457 into 10 to the power minus 3. So dt comes somewhere around how much? Sorry. This is the epsilon, no? Sorry, I did a mistake here. Okay. So this is the engineering stress. dE. E equal to L2 minus L1 upon L1. 15 minus 10 divided by 10. It should be 0.5. And the true strain is given by epsilon ln 1 plus E. So epsilon L 1 plus 0.5, it comes out to be 0.405. Okay, so if we put this value here, so what we'll get? dt equal to 0.405 divided by 4.457 into 10 to the power minus 3, and this dt should come where around 91 seconds. this is the value of the time taken by the polymer rod to extend from 10 mm to 15 mm at a temperature of 100 degree centigrade. So now coming towards our next question. During the creep under constant stress, the strain rate increased by a factor of 1.43 when the temperature was increased for 800 Kelvin to 805 Kelvin, and they are asking us to calculate the activation energy assuming the equations given in 1 and 2. So we need not to use the equation. They have given the equation here, and for that equation, we need to find out the activation energy. So please try to solve this. Okay, let's. So first we'll write the what are the things that has been given. So what they have given that during the keep under constant stress, the strain rate increased by a factor of 1.43. So the epsilon 2 dot is 1.43 times greater than epsilon 1, and the temperature was increased from T1 is given as 800 Kelvin and T2 is given as 805 Kelvin. Okay. And they are asking us to find out the value of Q, and R is 8.314 joule per mole Kelvin. Okay. So what they are asking us to calculate the activation energy, and they are asking us to use the equation 1 and equation 2. So first we will solve for the equation 1. The equation is given as epsilon dot equal to A by T exponential of minus Q by RT. Okay. So if I write this for the case epsilon 1 equal to A upon T1 exponential minus QI R upon T1. Let's say this is my equation 1, and epsilon 2 equal to A T2 exponential of minus Q by R T2. Let's say this is my equation 2. So now if I divide equation 1 by equation 2, so what I will get? That is epsilon dot 1 divided by epsilon dot 2 should be equal to A upon T1, A upon T2 into exponential of minus Q upon RT1 divided by exponential of minus Q upon RT2. So this AA gets cancelled out, and we'll get an equation something like this. That is epsilon 1 dot divided by epsilon 2 dot equal to T2 by T1 into exponential of this Q by R comes out comes out and comes outside, and we'll get 1 upon T2 minus 1 upon T1. So, and we need to find out the value of Q. So I will take a log on both sides. So what we'll get ln of epsilon dot 1 into T1 divided by epsilon dot 2 into T2 equal to Q by R 1 upon T2 minus 1 upon T1. So here we'll get ln. This is 1 upon 1.43 into 800 divided by 805. T1 is 800 and T2 is 805. Into R is how much? 8.314 divided by 1 upon T2 is how much? 805 minus 1 upon 800 equal to Q. So Q will be equal to how much? So it will come somewhere around 390 kilojoule per mole. Okay. So this is for our condition, means equation 1. That is the activation energy is 390 kilojoule per mole. Now we need to solve for the equation 2. So let me write down the equation 2. So like for second equation, the equation is something like this: epsilon dot equal to a sorry, it's b exponential minus q by rt. B exponential minus q by rt. So here, if we compare the equation 1 and 2, the difference here is this one, that t. Here t is there and here t is not there. So the final equation, if you see, these t terms will not be there in equation 2. And all other equation will remain same. That is ln epsilon 1 dot divided by epsilon 2 dot should be equal to q by r 1 upon t2 minus 1 upon t1. So if we rearrange, we'll get r into ln ratio of the strain rate divided by 1 upon t2 minus 1 upon t1. So in this case, we'll get 1 divided by 1.43 and 1 upon T2 minus 1 upon T1. T2 is how much? It is 805 and T1 is 800. So we'll get the value of Q somewhere around 383 kilojoule per mole. Okay. This is the second question by following the second equation. So now moving towards the next question, probably today's last question. So if the strain rate obtained at 500 degrees Celsius is 1 into 10 to the power minus 5 for pure aluminum with an activation energy for cell diffusion is 120 kilojoule per mole, the strain rate obtained at 600 degrees Celsius is. This is the straightforward question. Please try to answer it. So anyone? Okay, so let's solve. So we'll first write down the given data given, get the data given in the problem. So T1 they have given as 500 degrees Celsius, and the strain rate is 1 into 10 to the power minus 5 per second. Okay, and the activation energy Q is given as 120 power 3 joule. Okay, and they have given the T2, that is 600 degrees Celsius, and which is around 873 Kelvin, and this is 773 Kelvin. Okay, and they are asking us to find out the epsilon 2. So we'll use the equation, that is epsilon dot equal to A exponential minus 120 into 10. Sorry. We'll use the equation, that is the combined effect of strain rate and temperature. Epsilon dot equal to A exponential of minus Q by R T. So for first condition, we'll use epsilon dot 1 equal to A exponential minus Q by RT. So epsilon dot 1 is 1 into 10 to the power minus 5. A is unknown, exponential minus 120 into 10 to the power 3 divided by R is 8.314 into T1 is how much? T1 is 773 Kelvin. So from this we'll get a value of A. So A should come somewhere around 1286. So now we know the value of A and we know the value of Q and RT. Now we need to find out the epsilon 2. It is just a straightforward question. Just try to answer it. So we'll use again the same equation, that is epsilon dot 2 equal to A exponential minus Q by R T2. Epsilon dot 2 equal to 1286 exponential of into exponential of minus 120 into 10 to the power 3 divided by 8.314 into T2 is how much? 873 Kelvin. So epsilon 2 dot, that is the strain rate, should come around 8.49 into 10 to the power minus 5. So with this question, we'll end our today's session here itself. I hope you are practicing, and thanks for coming, and wish you all the happy Holi. So if you have any questions, you can ask. Otherwise, I will end our session here itself. So no questions. So we'll end our session here itself. So thank you for attending, and wish you a happy Holi.